Asymmetric cryptography is heavily used by the most secure systems such as distributed ledger technologies like the blockchain. So by understanding the math that led to the creation of asymmetric cryptography, you will have a good foundation that will later make it easier to understand complex terms and notions. Unlike symmetric cryptography, asymmetric cryptography does not reuse the same key used in encryption for decryption. Instead, it uses different keys. Asymmetric cryptography has three different categories. First, DLP, which stands for the discrete logarithm problem, and elliptic curve cryptography, and finally, RSA. Now you might be asking, why do we even need asymmetric cryptography? Isn't symmetric cryptography already enough for us? But you might have noticed that for Alice, for example, and Bob to share a secret that the evil won't capture, they need to negotiate on a certain key. Now, the operation of exchanging the key is where the evil tries to focus his efforts to get this key and expose all future conversations. What's even worse is that what if Alice has more than one connection? What if he has millions of connections? It could be, for example, a website that connects with millions of people. So he needs to have a separate key for each connection. Now Alice needs to maintain millions of keys for each connection, and each key exchange step has the probability of exposing the key by the hacker. The following diagram illustrates the mechanisms of asymmetric cryptography. Alice first generates two keys. The blue is the public key and the yellow is the private key. He sends the public key to everyone. Alice clients encrypt their messages with the public key and send all of those encrypted messages to Alice. Keep in mind that the hacker right here has both access to all of the encrypted messages and the public key. Alice decrypts all the messages with the yellow key, which is his private key. Now notice how efficient asymmetric cryptography is, because the Alice needs to keep track of only one key pair instead of maintaining millions of keys. We'll first try to understand some mathematical concepts and algorithms, such as EA, which stands for the Euclidean algorithm, the extended Euclidean algorithm, and the modular inverses, and the Euler's tangent function. We'll try to combine these to create our own simple asymmetric crypto system that uses one key for encryption and another key for decryption. Understanding these concepts is crucial and necessary because tomorrow you could be in charge of a team that has cryptographers, and you need to at least understand the challenges that are facing these cryptographers, or you could be using their APIs. And as we will see later, we will try to use some of the most famous APIs. So we need to understand these problems to have a good foundation that will make manipulating the most used libraries easy for us. Let's start with the Euclidean algorithm. The Euclidean algorithm was created to find quicker ways to solve the GCD of two numbers. So if we have GCD, which stands for the greatest common divisor, R0 and R1. GCD of R0 and R1 is about finding the greatest common number that can both divide R0 and R1. So if we have, for example, R0 is equals to 12 and R1 is equals to 6, a quick way to find the greatest common divisor of 12 and 6 is by factoring 12 and 6. So 12 is equals to 2 times 2 times 3. And 6 is equals to 2 times 3. What we can do next is we multiply the highest common prime factors. For example, here we have the highest common factors are prime factors are 2 and 3. So we multiply 2 by 3 and we get 6. Now you could have said that we don't need all of these steps to find the greatest common divisor of these two numbers, because the answer is quite intuitive for small numbers. But what if we have big numbers? Now factoring is a little bit hard for big numbers, and that's what the Euclidean algorithm was set to solve. So the Euclidean algorithm tries to solve finding the greatest common divisor for big numbers by reducing the problem to a smaller problem. Let me explain. So the GCD of, for example, let's say 27 and 21 is equals to the GCD of 27 mod 21 with 21. 27 mod 21, GCD of 6, because 27 divided by 21 would equal to 1, and the remainder would be 6. As we already said previously, the mod operation is about the remainder of a simple Euclidean division. So 6 with 21. So we reduce the bigger problem to a smaller problem. And the GCD of 6 and 21, GCD of 21 mod 6 with 6, because 21 is bigger than 6. So 21 mod 6 is equals to 21 mod 6. We divide 21 by 6, we get 3, and the remainder would be 3. So it is 3 with 6. And the GCD of 3 with 6 is really easy. It's 3. So 3 is the greatest common divisor between 27 and 21. Notice how the problem of finding the GCD was a little bit hard. Then we reduced it to a simpler problem from 27 with 21 to 3 with 6. If that seemed a little bit hard, here's another way of explaining the Euclidean algorithm. We say that the GCD of 27 and 21, so we first take 27 and we say 27 is equal to 21 times a number plus a remainder. Now 27 is equal to 21 times 1 plus a remainder, that would be 6. Then we take the divisor and we make it as the new dividend and the remainder as the new divisor. So we say 21 is equal to 6 times 3 plus 3. Then we do the same step again. We take 6, we put it right here, and 3 and put it right here. So we say 6 is equal to 3 times 2 plus 0. Now once we reach 0, we already know that 0 is not the greatest common divisor. So we go back one step further, one step back, and we say that 3 is the greatest common divisor. Okay, so we'll have another example. Let's say GCD of 56 with 15. At this point, I know you are saying, just let me do some JavaScript and mint some NFTs. Well, I promise it will be worth it. So let's say 56 is equals to 15 times a number plus a remainder. So 56 times 3, that would be 45, and the remainder would be 11. Then we take this right over here and this right over here. We say 11, we say 15 is equals to 11 times 1 plus 4. Take this right over here and this right over here, and we say 11 is equals to 4 times 2 plus 3, and then we take this right over here and this one here. 4 is equals to 3 times 1 plus 1, and 3 is equal. 1 times 3 plus 0. Obviously 0 could not be the answer, so we go back one step further and we find 1. So the greatest common divisor between 56 and 15 is 1. In this case, so this is a general rule. Whenever we have the GCD of R0 and R1 is equals to 1, we say that R0 and R1 are relatively prime. So the greatest common divisor between both of them is 1, so they are relatively prime. We will need this. This is a really interesting property that will help us construct secure asymmetric system. Now the extended Euclidean algorithm. It is an extension of the Euclidean algorithm in that it helps compute the coefficients of Bézout's identity, S and T. So these are some really big and weird words. Bézout's identity, ST. I promise this is really simple, and we will use all of these to construct our simple asymmetric algorithm. Just be patient. So the coefficients of Bézout's identity S and T states that whenever we have two numbers R0 and R1, we always have two other numbers S and T, such that R0 times S plus R1 times T it will always be equal to the greatest common divisor between R0 and R1. For example, we need to find S and T such that if you have two numbers 56 and 15, 56 times S plus 15 times T will be equal to the greatest common divisor between 56 and 15. I promise. We will use all of these. None of this will be just talking math just for the sake of it. Okay, so our goal is to find the two numbers S and T such that 56 times S plus 11 times T will be equal to 1, which is the GCD. So we first just do the regular Euclidean algorithm, then we need to rewrite it. We just say 56 minus, we just take all of these into the other side of the equation. So automatically when we take this to the other side, the signs will change. Just a quick way to remember it, just turn on the equal signs into minus signs and the plus signs into equal signs. Minus 15 times 3 is equals to 11, and 15 minus 11 times 1 is equals to 4, and 11 minus 4 times 2 is equals to 3, and 4 minus 3 times 1 is equals to 1. Okay, so we have this final equation right here, and we have 1 on this side. Now we just compare this with this. So we need to preserve this side because it already is the same. And we need to modify this side such that it will finally look something like 56 times a number plus 11 times a number. Okay, so how do we do that? We start from the last part of the last equation from the rewrite. Say 4 minus 3 is equal to 1. Now we notice that we have both the definition for 4 and 3. 3 is equal to 11 minus 4 times 2, and 4 is equal to 15 minus 11 times 1. We start from the rewrite, going step by step backward, substituting numbers. 3 is the first one we start to substitute, so we say 4 minus 11 minus 4 times 2 is equal to 1. We can simplify this. 4 minus 11 plus 4 times 2 is equal to 1. Now notice in here we are careful. We don't haphazardly subtract, add, or multiply, because we need to be careful. We need this 4 right here, and we need this 11, and so we need to substitute it. So we have 2 4s and another one, and that makes 3 times 4 minus 11 is equal to 1. Now we have 11 and 4, and both have a definition, but we start with 4. We substitute the 4, so we say 3 times 15 minus 11 is equal to 1. Now 3 times 15, let's simplify this. Minus 3, 11 minus 11 is equal to 1. As we said, we care about this 11. So we say 3 times 15 minus 4, 11 is equal to 1. Now let's substitute 11. Say 3 times 15 minus 4, and 11 is equal to 56 minus 15 times 3 is equal to 1. Let's simplify it. 3 times 15 minus 4 times 56. Now we don't multiply 4 by 15 because we need it. We multiply 4 by 3 instead because we already substituted 3. So that would make plus 12, 15 is equal to 1. Now we have 3 15 and 12 15. That makes 15 times 15 minus 4 times 56 is equal to 1. And there you go. We have S is equal to minus 4 and T is equal to 15. Now the final piece of the puzzle, modular inverses. So if we have, for example, two numbers, let's say n is equal to 7 and a is equal to, let's say, 3, such that n and a are relatively prime, which means that the GCD of 7 and 3 is equal to 1, which is the case because 7 and 3, their greatest common divisor is 1. There exists a number called the inverse of a, such that a multiplied by its inverse is equal to 1 mod n. So in this case, there exists a number 3 times a times its inverse is equal to 1 modulo 7. Let's try and find this number. We already know that 3 times 2 is equals to 6. That's less than 7. So let's start with 4. 3 multiplied by 4 is equal to 12 mod 7. That's 2 mod 7, and that's not what we are looking for. We are looking for 1. So 4 is not the answer. Let's increment. 3 times 5 is equal to 15 modulo 7 is equal to 1. And that is the answer, because 15 divided by 7, that gives us 2. 2 times 7 is equal to 14. 15 minus 14 is equal to 1. So the inverse in this case is 5. We can choose some number b, and b should be less than n, and if we transform b by multiplying it by a, that would give me a number, let's call it c mod n. Now what if I want to take c and transform it back to its original number, which would be b, because I took b and I transformed it. Now this transformation is simple in this case. It's just a multiplication by a, so I got c, Now, the cool thing is that I can take C and multiply it by the inverse of A, and I would get back B mod M. Let's have an example. Let's say B is equals to 4. I multiply 4 by 3, I will get 12. 12 mod 7, that would be 5. Now, I successfully transformed 4 into 5 by multiplying it with A. Now, what if I have only 5? So I start from 5 and I want to go back. So I multiply 5 by the inverse of A, that would be 5. And that would give me 25 mod 7, and that would be 4. Now, this looks like encryption and decryption. So you can say that I encrypted 4 by multiplying it by A to get 5, and then I decrypted 5 by multiplying it with the inverse to get 4. Now you might be thinking, what do inverses, or the Euclidean algorithm and the extended Euclidean algorithm, have anything to do with our purpose of today, which is to create an asymmetric algorithm that has two keys. The first key we use for encryption, and the second key should be different than the first, and that is used for decryption. Okay, so we first start by selecting two numbers. The first number should represent the number of elements in our group. We call it n. And another number, let's call it e, which belongs to n. We verify if these two numbers are relatively prime, which means an inverse must exist such that e times d is equal to 1. How do we verify that they are relatively prime? We just use the Euclidean algorithm, because in big numbers we already said that it is hard, but using the Euclidean algorithm it will be easier. After verifying that the two numbers are relatively prime, it means that there is an inverse, as we said, d. Now, I could say that e is the public key that I give to anyone for encryption, and the modular inverse is the private key. It's d. So that people can encrypt messages using the number e, and then I can decrypt the message with its inverse, which is the private key that I keep private. The extended Euclidean algorithm will help us find the inverse of e. So let's see a practical example. We first select a number that represents our group and should be bigger than 0. Then we choose e that belongs to m. We verify that e is relatively prime with m. We calculate the inverse of e using the extended Euclidean algorithm, and we encrypt m with e using the encryption formula c is equal to m times e mod n. We decrypt c using the private key, using the decryption formula, which is m, the message, is equal to the ciphered message times the private key mod n. Let's have an example. We first start by selecting two numbers, n and e, such that e belongs to n is equal to 11, and e is equal to 5. We need to verify whether these two numbers are relatively prime or not. And then we calculate the inverse if they are relatively prime. We do the steps as we explained before. We find out that using the extended Euclidean algorithm, remember, it will help us find the two numbers such that 11 times s plus 5 times t is equal to 1. We find out that 9 is s and 4 is t. But we can quickly eliminate this, because any number A times n mod n would always be equal to 0. So I have 9 times 5 is equal to 1, which means the inverse of 5 is 9. Now we proceed with the final step, which is encryption and decryption. So we encrypt M using the encryption formula, and then we would get C, and that is 7. And then we send C, and the owner of the private key would be able to calculate M using the decryption formula. The problem is that anyone who participated in this bootcamp now knows about our big secret, which is the extended Euclidean algorithm. So anyone could easily hack this algorithm by simply calculating the inverse D using the extended Euclidean algorithm. So we need a way that allows us to easily create the public key pair, both the public key and the private key, using some special information. And without this special information, it would be harder to retrieve or calculate the private key. Now, we always have hard problems in mathematics. So there are some hard problems in mathematics that we can use and exploit to create such an algorithm. In other words, we need some sort of a function that will allow us, let's call it f, that when we give it some secret information that shouldn't be shared to anyone, will give us the public key. But given the public key, you could not infer S, or it would be very hard to get the secret information that I used to generate this public key. And these functions are called one-way functions. We will study one of these one-way functions tomorrow, inshallah.